In this video, we will be talking about combustion analysis. This method supports our earlier learning objective for determining the empirical and molecular formulas for compounds. So combustion analysis takes advantage of the fact that hydrocarbons always produce carbon dioxide and water as the products. And so if we take our sample that contains carbon, hydrogen, and maybe some trace amounts of other elements found in organic compounds, we can burn that and collect all of the carbon dioxide that comes off and all of the water that comes off. We can pre-weigh these collection containers so that we can subtract to figure out what mass of water was obtained and what mass of carbon dioxide was absorbed. And then the other gases will come off. If we know the mass of this originally, we can do some subtraction in order to figure out what amount of this original sample was due to other elements within the sample. So here's a general flow of how these calculations are going to go. We're going to start off with our mass of carbon dioxide and our mass of water, convert that into moles of carbon dioxide and moles of water. Then, based on the subscripts in the chemical formula, we will find our moles of carbon and moles of H. Once we know the molar ratio of all the elements within the sample, we can find the mole ratio, and then that gives us our empirical formula. If we also know our moles of carbon and our moles of hydrogen, we can figure out the original mass of carbon and the original mass of hydrogen in the original sample. We can also use that to figure out the mass percent composition of the original sample. So here's an example problem. It tells us the 12.915 gram sample contains only carbon, hydrogen, and oxygen. And so it's burned in excess oxygen to yield 18.942 grams of carbon dioxide and 7.74 grams of water. So I'm supposed to find the empirical formula of this compound. I know that carbon dioxide can help me figure out the mass of carbon, and the mass of water can help me figure out the mass of hydrogen, but then I still don't know what mass of oxygen I had in the original sample. Since I'm reacting with oxygen, I cannot figure out the mass of oxygen from the carbon dioxide and water's mass of oxygen, because that's not all oxygen that came from the original sample. Some of it came from this. So I'm going to have to use the law of conservation of mass once I find the mass of carbon and hydrogen in order to subtract that from the original sample to figure out how much oxygen was in the original sample. This will take a while. This will be fun. Okay, so the first thing we need to do is figure out how many moles of carbon we have in this 18.94 grams. To do that, I have to divide by the molar mass, which is provided up here. And so it's 44.011 grams per 1 mole carbon dioxide. That's a 0. Based on the subscripts in the chemical formula, 1 mole of CO2 gives me 1 mole of carbon. So let's go ahead and type this into the calculator. 18.942 divided by 44.011 is 0.430392. And I'm going to store this number as A. Now whenever I need that number, I can recall the letter A and use that number. Now I have 7.749 grams of water, and I can convert that into moles. 18.016 grams per mole. And based on the chemical formula, for every 1 mole of water molecules, I'm going to have 2 moles of hydrogen. So let's type that into our calculator. 7.749 divided by 18.016 times 2 is equal to 0.8623 grams of hydrogen. And that was grams of carbon. It's not grams, moles. Moles. We're in moles still. Moles. All right, and now I'm going to store this number as B. I'm going to store that number as B. What the heck was that? That's not what I meant to do. Oh dear. All right, now that I have both of these numbers stored in my calculator, I can convert these numbers into grams in order to figure out how many grams of carbon, grams of hydrogen I have, and then I can work out my mass of oxygen. I know that this 12.915 grams is going to be equal to my mass of carbon plus my mass of hydrogen plus my mass of oxygen, because that's the total. So I can take my 0.430392 moles of carbon and convert that back into grams. That is 12.011 grams for every 1 mole. And so I can do alpha A to recall that number. All scientific calculators should have the ability to store numbers, so you should learn how to do that on your calculator. And then that's going to be in grams of carbon, and so that's my 5.1694. I'm going to store that as C in my calculator. Okay, now I got to do the same for my hydrogen. That's not what I meant to type in. Well, my eyeballs were looking at the wrong thing. Need to type in my moles. So that's 1.008 grams per 1 mole. And so that's going to be my alpha B times 1.008. And so that is 0.867117 grams of H. 0.867117 grams. Subtract both of those from the 12.9, and so your mass of O will be 12.951 minus that previous answer for the mass of hydrogen minus my alpha C value, which is my carbon. And so that tells me my mass of oxygen is equal to 6.8784 grams. So now I got to convert that into moles so that I can start doing my empirical formula. And so I can 6.8784 grams of O, got to divide by the molar mass in order to cancel out grams. 15.999 grams 1 mole. And so that's going to be equal to 0.4299 moles of O. So now my tentative chemical formula is carbon with 0.430392, hydrogen 0.86023, oxygen with 0.4299. Gotta divide by the smallest, which in this case is the oxygen. And so then we're left with carbon. That's going to be about 1 because they're so close together. Hydrogen, I want to make sure that that is 2, but it looks like it's going to be about 2. And oxygen is going to be 1 for sure. I can store this number. Ah! How do I get that number back? Okay. Store as alpha D. Okay. So I can do, that was A. So if I do alpha A divided by alpha C, that's going to be about 1. So B divided by alpha C. No, that's not, that can't be right. What is C? Is C just whatever the previous answer was? That's not what I just wanted to see. Or no, I was D. D is what I was doing. So, kind of alpha D. No wonder things are off. Yeah, that's about 1. So, this value was stored as D. That was A, B. Might need to write these things down eventually. So alpha B divided by alpha D is 2. So 2. So my empirical formula is CH2O. Here's a practice problem for you. Go ahead and pause the video and try to work out the empirical formula for a compound made out of 33 that produced once in combustion analysis 33.057 grams of carbon dioxide and 10.816 grams of water. Unpause the video when you are ready to continue. All right, let's get going. So we know that we got to convert between our grams of CO2, get that into moles of CO2. That will get us into moles of carbon. So we have our 33.057 grams of carbon dioxide, and the molar masses are up here. So we divide by the molar mass in order to get moles of carbon dioxide. Now for every 1 mole of carbon dioxide, I have 1 mole of carbon. That's based on the subscripts in the chemical formula. And so this is 33.057 divided by 44.011, and that gives me 0.751107 moles of carbon. Now I can do the same for the water. 10.816 grams of water divided by 18.0816 grams gets me into moles of water. For every 1 mole of water, I have 2 moles of hydrogen. So I'm going to store this number. Okay, stored as A. Remind myself. All right, now we got the 10.816 divided by 18.016 times 2, and that is 1.20071 moles of H. And so now I can store that number as B. So I can write out my tentative chemical formula where I have 0.751107 carbons and 1.20071 moles of hydrogen. The carbon is the smaller of the two, and so I'm going to divide both sides by the smaller amount. And that would make my carbon equal to 1 because any number divided by itself is 1. And now I got to divide that number on my calculator by 2, by the carbon, and that gives me 1.598. And so this value is really close to about 1.6. 1.6 is 6/10, which is equal to 3/5. So this is 3/5. If I want this to be a whole number, I have to multiply by 5 in order to make this cancel out and be 3. But there's a 1 up there too, so if I multiply by 5, I should be getting to a whole number. So 1 times 5 is just 5. But what's this number times 5? That is 7.99, which is essentially equal to 8. So our empirical formula is C5H8.